Our last speaker for this session and for today is David Whetter. David is the founder and president of Agri-Earth Consulting Limited, a firm established to add value and provide environmental solutions to agriculture across the Canadian prairies and beyond. David is a pedologist, agroecologist, and registered professional agrologist with 25 years of consulting experience in agriculture, environmental planning, permitting, and management. His technical focus is on the soil landscape environment, agriculture management systems, and agricultural water management. His core experience is in agriculture irrigation, drainage, and soil salinity. And David's title today is Soil Salinity and Tile Drainage, Desalination Dash, or Manitoba Marathon. Did I get that right?
Well
okay.
Done.
Thank you.
Okay, thanks, Curtis. Okay, I'm happy to be here today to talk a little bit about soil salinity and tile drainage. I think both of these subtopics have some misconception around them. So I hope to shed a little light on both of these topics and bring a little science to the discussion. And then in terms of bringing them together around the response of soil salinity to tile drainage, maybe try and get at the answer to this question, desalination dash or Manitoba Marathon. And John, I had you in mind when I came up with this title, so hopefully I get a thumbs up. And I realize I'm the last speaker, the only thing between all of you and a refreshment, so I'm going to hopefully make it worth your while here. Having said that, so soil salinity and tile drainage meet at a bar after a few drinks and some good conversation. They're really, starting to make a connection. Tile drainage, who most consider passive, musters up the courage to say to soil salinity, hey, soil salinity, I'm feeling like we could really, be something together. The dynamic and sometimes severe salinity responds, yeah, okay, whatever. Trying to take it to the next level, tile drainage says to soil salinity, no, I think what I need to do is get underneath you. And unfazed, soil salinity responds dryly, sure, but then we need a long shower. Okay, so just in the way of the agenda here, I told my 12-year-old daughter that I was going to tell a dad joke about soil, and she's like, no, don't do it. Anyway, I'll start off with, again, a little basic overview of soil salinity, and then I'll talk very briefly about tile drainage for those that may not be familiar with the practice. And then, again, I'll bring those two together, in terms of a field setting, not a chat GPT envisioned bar. And I'm going to close today with a brief discussion on some soil salinity monitoring work we're doing at the Souris Plains Soil and Water Management Site at Hartney. So this is kind of a soil salinity 101 mini course, and I am just note that Tom DeSutter, for anyone that was here in 2023, Tom DeSutter gave a really good presentation, kind of diving into a little more detail on soil salinity than I'm going to. So if you find some of what I'm saying interesting, I recommend you go back and check Tom's presentation for a little more detail there. So at the basic level, a salt is it's a compound formed when an acid and a base come together. They form an ionic bond. That salt crystal is not, even though we're seeing a lot of salt crystals at the soil surface there, it's not the salt crystal that's the concern. It's when that's solubilized and you have ions in solution. And what happens is those ions essentially compete with the roots for water, right? So the more salt ions you have in solution, the more competition essentially it's giving to a plant root to pull that water out of the soil. In the context of agricultural cropping, soil salinity is simply the accumulation of those soluble salts and two concentrations that are impactful in a negative sense to crop growth, productivity, and crop yield. So salts can occur naturally in our soils, and that's what we consider primary salinity. However, I think a bigger issue in Manitoba around management of our fields is what we call secondary salinity. And this is salinity that's caused by some human-induced change in our landscape. So, we've all driven down Trans-Canada Highway or other highways. We can see salt crusting like in the picture along the ditches and edges of roadsides around other linear developments as well. So that would be an example. And then another thing that we've done over the last 100 years is convert our Canadian prairies from permanent grasslands to annual cropping. And that's really shifted that water balance in our fields, and that's been a major cause of this secondary salinity as well. So there are two conditions, I borrowed this from Manitoba Agriculture, two conditions required for this soil salinity, and this, again, we're talking about secondary salinity here. Two conditions we need. The first one is the presence of soluble salts, and that can be in the subsoil or in the groundwater, or typically it's in both. And then we need high water tables, and what that means is kind of anywhere within around 6 feet, that water table approaching the soil surface. We're getting into that condition where that water table and this capillary fringe, which I'll talk about in a minute, is starting to interact with our crop rooting zone in the soil surface. So you really need this high water table condition to get that secondary salt buildup. Really when we talk about soil salinity, it's a water problem, not a soil problem. Right, Marla? Thumbs up from Marla. Okay. So far, so good. So this is important. In terms of understanding how to manage soil salinity, we must understand how that water is moving in and through our soil. And water really moves two ways, right? So it's downward by gravity, and then laterally and upward by what we call capillary action. So that's the kind of the drying up or that suction action that our unsaturated soils impose on a saturated soils or saturated zone below. I have a conceptual diagram up on the screen here. This is just showing kind of one example of some of the many kind of salinity development mechanisms we have across the prairies. And essentially what we have here is we get rainfall water recharging through, say, like an upland area of the landscape, collecting soluble salts as it goes, maybe enters the shallow groundwater, and in this case that shallow groundwater is flowing kind of laterally down slope. So above this water table, which is represented by that solid blue line, you get that capillary action, pulling water up from that saturated water table and pulling it upwards towards the soil surface. So that zone of capillary action we call the capillary fringe. So that's in that blue hatched area above that solid blue line. So when we get to a point in the landscape where that capillary fringe is interacting with the soil surface, then we get evaporation pulling that water up and evaporating off, and we get any of those soluble salts in that water accumulating and depositing at the soil surface. And you get unhappy plants, obviously, as a result. This image here is from Agriculture Canada. It just shows the risk of soil salinization across the prairies from 2016. Honing in on Manitoba, we've got lots of areas in that kind of low to moderate to high salinization risk. And, it's a big problem. 1 million hectares across the prairies had a moderate to severe salinity. That was numbers from 2006, so not a small area. In 1980s dollars, that equated to around $260 million in lost revenues, which would be about $650, $700 million in today's dollars. So, not a small problem from an annual crop producer's perspective. So how does soil salinity affect a couple of our major field crops in the prairie region? Go into some data here from NDSU, North Dakota. And on the left-hand side of the screen, we have canola, and right is wheat. And we have relative yield on the vertical or y-axis. And then we have electrical conductivity, which is a measure of our soil salinity on the x-axis. So when looking at canola and going from the blue line to the gold line, that's about a 30% decrease in crop yield. And for canola, that equates to about a 1.5 to 2 unit electrical conductivity increase reported on a fixed ratio extract here. I'll get to that. When you look at wheat, that same kind of 30% reduction happens over about a 3 unit increase in electrical conductivity. So different crops have different sensitivities, obviously, to salinity. And you can see why producers may be motivated to look at ways to reduce salinity. A small change in salinity can be a pretty significant change in crop yield. I'll just do a quick little shift here into sodic soils or salinity soils. So this is a specific salt-affected condition where soils have a high concentration of sodium relative to other cations like calcium, magnesium, as two of the major ones. So when we get an accumulation of sodium or these sodic conditions, we can get degraded soil structure as our clays disperse. So in that cutaway picture of the soil profile there, you see this hard pan, this BNT horizon we call it, and kind of essentially cements over that layer, really causing problems for downward water movement through the profile and root development as well in extreme cases. So there's really three options in terms of dealing with sodic soils, and number one is just to leave them alone. I think they were meant to be in grasslands, and you just leave them in grasslands and have a managed grazing system if you have livestock. Number two is you work with them, you grow sodium-tolerant crops. As an example, wheat, oats, and rye, I think, have around an 8 to 12 SAR unit threshold. So if you keep that in mind on the slide I have down the road here. But fairly limited as well in terms of productivity. Or you reclaim them, which is expensive and takes a lot of time. It involves applying amendments to try and kick that sodium off the soil exchange and then finding a way to leach that sodium out of the profile. Okay, most of the sodic soils in the prairies occur in Alberta and Saskatchewan. However, we do have some in Manitoba. Not such large areas as we have in the other prairie provinces, but we do have them south of Winnipeg and in the southwest region, kind of around and west of Brandon. I think the message here, when we start talking about tile drainage, is when it comes to considering tile drainage, you have to know what you have, right? So it's not just a salinity limitation. You have to understand if that acidicity is a limitation as well. Acidicity is more challenging than salinity to identify in the field and to assess that degree and extent. So it takes a little more effort. But sodic soils typically occur in association with saline soils, so just make sure to include sodicity as part of that detailed salinity assessment that you should be doing prior to making tile drainage decisions in saline soils. So, just a couple caution flags specifically to sodic soils with tile drainage. If you have a straight sodic soil, so that's one where you might have these structural issues, it can really affect the performance of your tile drainage system, right? Preventing that downward water movement to get into the tile. And then when we have a situation called a saline sodic soil, so that's high sodium but also high bulk soil concentrations, then there is a cautionary flag there as well that under tile drainage and that drainage on steroids, if you will, or that shift in the drainage through the soil profile, we can actually, in certain situations, reduce the bulk soil salinity, but if that sodium stays behind, then we can actually drive that into a sodic situation. So this is a table just again pulled from Manitoba Agriculture Soil Management Guide, I believe, and it shows you the thresholds, so the electrical conductivity thresholds for salinity, as well as the SAR thresholds. So essentially any EC value in our soil over 2 is considered saline for pulse and soybean crops, and anything over 4 is considered saline for all other crops, recognizing difference in crop sensitivities. When it comes to sodium, these SAR units, anything over 13 is considered sodic. So when you have a soil that's over that SAR threshold, but below the EC threshold, that's where we're considered a sodic soil. And again, that's kind of that red flag for tile drainage. Where we have the SAR unit over the threshold, but also those soils are considered saline. That's getting more into that yellow flag area. Important note there in red is know your lab electrical conductivity method. These, for example, these thresholds are presented in saturated paste EC values, and that's kind of mimics what our plants experience. So that's kind of the standard. A lot of our agricultural soil tests report on a fixed ratio extract. It might be 1-to-1 or 2-to-1. So know the method. Fixed ratio extracts need to be converted to a saturated paste equivalent. in order for them to be comparable with things like these thresholds. Good news with salinity is we do have assessment tools, things like EM38, Veriscart. When you calibrate it with soil samples, you can develop nice degree and extent of salinity maps. Again, for sodium, sodicity, you've got to rely on those soil test results. Okay, so how do we manage soil salinity? Well, again, we kind of don't, not directly. We manage soil water, right? And what does that mean? So there's kind of three main components to managing soil water for salinity, and that's number one, lowering that water table. So we want to bring the water table down to the point where that capillary fringe is interacting less with our crop rooting zone or the soil surface. We want to increase infiltration, so by lowering the water table, that opens up that opportunity for water to infiltrate, and there's other, obviously, management practices we can do, build our soil structure, that type of thing, which is really a pillar of soil health. And then the third thing is reducing evaporation, just trying to reduce that kind of pump that's pulling water up and out off the surface. So in other words, we're really trying to undo what we've done by converting from our permanent grasslands to our annual cropping management systems. And kind of that bottom line is the only way to really reduce salinity is to get at those mechanisms that are driving that secondary salinity development. So how do we do it? There's really only two options in my mind, and one is planting kind of, salt-tolerant species, deep-rooted perennials, and just kind of leaving it. And to me, the only solution there is a long-term, covering a lot of ground, and a long-term. Tom has a really good slide on this where they do large grass strips as part of their CRP program, and they monitor salinity there. So they took care of the salinity where they put the grass, but the salinity just kept moving into the field. But there's landscape specifics around that, obviously. The second option is tile drainage, and that's what I was asked to speak about today, so I'll move on and talk about that. So just as a very brief kind of overview of tile drainage, tile drains are simply perforated plastic pipes. The one shown here has that white sock around it to prevent silting. These tile drainage pipes are installed below the rooting zone, typically using a plow like the one in the video. And the runs in Manitoba are typically spaced around 50 feet. It seems to be the de facto spacing, but spacing should vary based on soil conditions, desired drainage outcomes, and then other factors like soil salinity. So generally, when we're talking about soil salinity, a tighter tile spacing will drain water a little faster and drain slightly higher volume. So at least in theory, if you have saline soils, a little tighter spacing than just based on what the soil conditions would direct you to, should remove more salt and more quickly. So tile drainage works by removing that saturation water from the crop rooting zone. So the figure on the left-hand side shows saturated soil condition, and you can see that water table is pretty close to the surface. Pretty unpleasant scenario for those crop roots, and has obvious implications for salinity. Back to the capillary fringe there and water table close to the surface. So here we have that same situation with tile drains installed. So the tile drains pull down that saturated zone to the level of the tile at the location of the tiles, and they create a mounded water table between the tiles. So a few slides back, I mentioned that water moves in two ways. So, downward by gravity and then laterally upward by capillary action. So tiles remove that gravity water. So that water that's above field capacity, the soils can't hold against the forces of gravity. So tile just creates that opportunity to let gravity bring that water down to the tile. This capillary action still happens above that water table, okay? So, what we're trying to do with tile drainage is bring that water table down so that it's not, drowning out our crops. But the desired kind of management objective is to keep that water table as close as we can to that crop rooting zone. There's research done in Manitoba showing, the benefit that shallow water table can have for our crops, particularly during periods of drought. And, placing tiles as close as we can to the surface while achieving our desired drainage outcomes is really kind of where we want to be in terms of water conservation. So, but I think there's maybe a little bit of a trade-off here in terms of water conservation and maybe trying to achieve salinity reduction. So it's kind of probably a little trade-off there. Okay. I think I got ahead of myself there a little bit, but so I think I covered this one off actually. I'll keep moving. So now we're going to talk about when we bring that tile drainage together in terms of response to soil salinity. So we just covered that salinity development mechanism there on the left. So I'll just show you when tiles are installed in that landscape conceptually. That's the little red dots in the figure on the right. So essentially those tiles pull down that water table, they bring that capillary fringe down, and they promote infiltration. The water table is no longer just sitting at the surface. Promote infiltration and allow infiltrating water to pick up soluble salts and bring them to the tile. And then of course that tile water is discharged typically at the field edge. Plants can reestablish and then they reduce that evaporation. So again, the three factors there in secondary salinity development is lowering the water table, increasing infiltration, and reducing evaporation. So that's why tile, in theory, is effective. So let's look at some data beyond theory. This is work done by Agriculture Canada around Winkler. So it's showing our salinity classes in green and orange in this case, weak and moderate salinity from 1995 when tile was installed in this field all the way to 2011, so 16 years. So you can see, looking from the upper left image there, 1995 all the way to 2011, you can, it's apparent there's been significant reduction in those weak to moderate salinity classes. And even, looking in kind of over 3 to 5 years, you can see that reduction occurring, but probably up to about 10 years before that kind of significant reduction happened. Going south of the border here, North Dakota, NDSU and AgVice have done a bunch of work on salinity under tile because they have lots of salinity and lots of tile. So this is showing 2 sites, salinity reduction over time, over, again, 16 years, coincidentally. 2 things to note. So that, it's clear there's been, a lot of salinity reduction over that 16-year period. But it's taken, I would say, a long time to get to that point where it's a significant sustained reduction. Like when you look at Site 2, you're probably looking at 10 years before really noticeable reduction in salinity in a sustained manner. And then, obviously high variation year over year. I'm just going to skip past the slide. It's kind of showing the same information. But again, that salinity's got to go somewhere. So, in terms of water quality, we have to think about what's coming out of the pipe. So anytime we're taking salinity out of the field, it's heading out of the pipe, we have to think about where that water is going, obviously, whether it's going overland, downstream, or into surface water. And I think, intuitively, over time, as you're reducing the salt in the soil, that salt concentration is going to come down in your discharge as well. But it's kind of I would say it's a soft area in the body of knowledge, and it's something that would benefit from some additional work. And that's when I segue into the Souris Plains Soil and Water Management Site, one of these on-farm projects funded by Manitoba Crop Alliance, Manitoba Canola Growers, and Paulson Soybean. So what we have is half-section field. We've got 3 field drainage zones in that gray shading there, and then we've got some research plots in that green and orange. So tile was installed in the fall of 2001. I should acknowledge as well the cooperating producer is Whetter Farms Limited. So I'll show you just a little couple slides here on salinity. I get the nod from Curtis here. We're monitoring soil moisture, we're monitoring water tables, we're monitoring surface runoff and tile runoff here, but also soil salinity. So on this slide here, we have calibrated the M38 salinity maps. The first one in the top right there was taken the year before tile was installed, so in the fall of 2020. And then in the bottom right is following 1 year of tile, so in the fall of 2022. No, just within those black lines. I'll just show you that in a minute. It's about half of the 320 acres is tiled. So a lot of that green area is not tiled. So the color symbology in the maps there, anything in yellow or orange or red is into that weakly to the moderately to strongly saline, so pretty impactful to crop production. When you hone in on these drainage areas in those hatched circles there, you can really see that reduction in that over that 1 year. Actually equated to 39 acres of land that came out of that weak to strong salinity into kind of a slightly to non-saline situation. About 22% of the tiled area. So very significant results for 1 year of tile drainage. But 2022 had a very high precipitation. It was very abnormally high. If you look at the table here on the left-hand side, it shows you rainfall from April to October. So that's kind of that period in which tiles are active. And then it's presented as a percent of long-term average over that period. So you can see in 2022 there, we had 135% of average, around 20 inches of rainfall in that period. If you look at the year before and the 3 years following that installation, or that year of that salinity monitoring, we've been at average or well below, right? So we were nervous. The tile was supposed to go in 2020, and we were pretty nervous because nothing would have happened in 2021, and very little has happened in the last 3 years in terms of tile flow. So you can see the tile flow volumes out of our 3 field management zones. When you look at the blue versus orange versus, I think it's green. It doesn't look green here, but you can see in 2022 we had very large volumes of tile flow relative to 23 and 24. So kind of in average conditions or less, we would expect very little flow, very little salinity reduction. So what happened in 1 year is probably what happens in 5 to 10 years, kind of under an average 10-year cycle. Okay, and I'll just wrap it up here. So I think tile drainage is an effective practice at reducing soil salinity, but it's a long-term process, typically, unless you install it in the fall of 2021. And it's variable, highly variable year over year. So you can get reductions and then it can bounce back. And know your limitations around salinity and acidicity before making that tile decision. Pre and post tile soil and water monitoring is important, highly recommended, and consider those downstream impacts. I'm just going to leave you, there's 2 QR codes here. One is a series of fact sheets specific to beneficial management practices to tile drainage in Manitoba, posted on PAMI's website, and then there's a QR code to the Souris Plains Soil and Water Management website. Thank you.
I guess we got time for 1 or 2 questions. We're at the end of the day, but we'll take them if you got one.
From Jacob, can soil shrink swell cycles and freeze-thaw cycles affect tile drains?
Shrink swell soils certainly do, yes. Yep. So that's, when you're getting into clay soils, heavy clay soils, we want to understand the nature of those clays. So certainly, in Red River Valley, for example, clays shrink swell properties, the Montmorillonites and smectite clays. So those can kind of swell and seal up and obviously affect tile performance. And related to sodicity, those are the soils that we're really concerned about. When you get high sodium in those shrink swell clays, that's where you can have real problems around the degraded soil structure. Freeze-thaw cycles, the only comment there is our soils are frozen for a long period of time, which really changes the hydrology compared to, say, what's happening in the US Midwest, where a lot of the body of knowledge comes out of. So our tiles operate a lot differently than in areas where they don't have to go through freeze-thaw cycles.
I have questions.
Alex, I'm going to use your approach, just back away.
Yeah, just start talking and leave. Yeah. So in that last example, envelope material, no envelope.
Sorry?
A sock or no sock? We call it envelope in Ontario.
At the research site?
At that most recent site?
Yeah, it has the sock in it. There's fairly high silt content.
Any issues with precipitation, plugging the envelope material or the tile itself?
Not that we're aware of. No.
Not that you've looked yet.
The biggest challenge we have at that site, again, it's related to the freeze. We have a lot of, we'll get that spring melt, and then everything will freeze down again, and we've had issues with ice plugging our lines, but not
Okay.
not the socketing.
And then follow-on question, because we have a lot of issues in some areas with iron ochre
Right,
growing in the tile. It's just like a biogenic iron material that'll plug tile up. But I didn't know if there was like because that sodic soil looks pretty gross. I imagine it looks pretty gross in the tile.
We don't have sodic
soils.
soils at the research site there, and again, we don't have many in Manitoba, but I've come across a couple that we've kind of flagged in western Manitoba that are kind of in that borderline. Yeah,
Thank you.
thanks.
I'm here. There. I'll run over to Terry. I was going to say, don't make me run down to the bottom and then run back up. This might be our last one here. We'll see.
So it's this is going to be a very general question, but it comes from my previous work before my current job. I'm from Beausejour. Soils are Red River Valley looks like light soil to us, right? Heavy soils, horrible subsoils. Clients up in Arborg, even heavier, unbelievable. Those are the areas where there's a lot of interest, right? Because all of the problems you outlined are ones that are there on steroids. But the fear is that they're heavy enough, the structure is bad enough that even tiles really aren't going to help. Very hard question to get an answer from anybody.
Yeah.
You know, like I helped organize the local ag conference and I had a whole slew of people come through. Nobody could really answer that question. A few people have tried a little bit of it and everybody's very ambiguous. So, but are there places where it's just not going to work?
It's a good question. Like obviously lots of heavy clays are drained. Like you go south of the border into North Dakota, lots of heavy clays are drained. We do have the PSA site. Manitoba Agriculture has the PSA site up in Arborg area. I think so. I'm not sure. I haven't heard what's happening there, but I know that it can be a challenge to get flow, effective tile drainage out of those soils because it's right. Yep. But I mean that's also the nature of tile drainage in our semi-arid or some humid environments. So the more limitations you have, then the less effective tile is going to be as a practice for you. But it's really knowing those site-specific conditions and until you get some in the ground, I guess in that area, you don't have that anecdotal evidence that it's working. But
Okay. Join me again in thanking David. Thank you. Oh, sorry, I'll keep that.